In the third lecture on material analysis by nuclear techniques, we shall discuss on neutron activation analysis, known as NAA in short. Neutron activation analysis is a nuclear process used for determining the concentrations of elements in a vast amount of materials. NAA relies on excitation by neutrons so that the treated sample emits gamma rays. It follows the precise identification and quantification of the elements above all of the trace elements in the sample. NAA has applications in chemistry but also in other research fields such as geology, archaeology, medicine, environmental monitoring, and even in the forensic science. The method is based on neutron activation and therefore requires a source of neutrons. The sample is bombarded with neutrons, causing the elements to form radioactive isotopes. The radioactive emissions and radioactive decay paths for each element are well known. Using this information, it is possible to study spectra of the emissions of the radioactive sample and determine the concentrations of the elements within it. A particular advantage of this technique is that it does not destroy the sample and thus has been used for analysis of works of art and historical artifacts. Neutron activation analysis is very sensitive and is therefore used to analyze minor elements which are present in very low concentrations. The method is especially useful for trace element analysis, example in high purity substances, and is therefore important in semiconductor techniques. It can also be used to detect trace element in water, biological material, and minerals. In archaeology, NAA can give useful information about the origin of the findings according to the so-called fingerprint of the individual element composition in their raw materials. It is usually used as an important reference for other analysis methods. Principle of the technique. Neutrons incident on a target material can undergo several types of interactions with the nuclei in the material. Elastic scattering is one such process. However, it is of not much practical value for elemental analysis. In inelastic scattering, also referred to as the N-gamma reactions, a part of the kinetic energy of the neutrons is taken up by the target nucleus, which gets excited to one of its excited levels. The subsequent decay of the nucleus results in the emission of a gamma ray photon. The gamma ray gives a quantitative signature of the particular nucleus of the target. In addition to scattering, a variety of nuclear reactions can take place. Thermal neutrons interact with nuclei predominantly via the radiative capture process, which is designated as N-gamma. Radiative capture is possible with almost all stable nuclei. However, the reaction cross-section varies widely from isotope to isotope. The compound nucleus will be in an excited state, and its subsequent decay to ground state leads to the emission of a gamma ray. Fast neutrons interact with the nuclei via Np, N-alpha, N2n, N' reactions. The outgoing particles or gamma rays are detected by a suitable detector. The type of the particle and its energy in most cases identify the isotope, and the number of such particles per radiation detected gives a quantitative estimate of the isotope. The number of detected outgoing particles is given by N equal to INT sigma 1 minus e raised to minus lambda Tr times e raised to minus lambda Tc minus Tr times omega d eta t. Here I is the incident flux of neutrons Nt is the number density of nuclei in the target, sigma is the reaction cross-section, and it is assumed that the irradiation is stopped at a time t equal to tr and the counting is done at time t equal to tc. Omega d gives the solid angle subtended by the detector at the target center, and eta is the detector efficiency. The constant T is a correction factor which is equal to 1 for detected charged particles. In many practical analytical applications, a comparison method is used. When samples are to be analyzed for a few elements, standard samples of these elements are activated at the same time as the actual sample and counted in an identical manner. This technique is considerably simpler as compared to the method depending on the available cross-section values, detector efficiencies, and neutron flux. In such cases, the elemental concentration in the sample can be calculated as the product of the elemental concentration in the standard with the ratio n sample over nst of the counts with the sample to that with the standard. We'll now discuss about the instrumentation. It essentially comprises of a source of neutrons, an irradiation chamber, a transport mechanism for taking the irradiated sample to the counting room, a detector, and an electronic setup for counting. Neutron activation analysis can be carried out by both fast neutrons as well as slow or thermal neutrons. And all sources of neutrons directly give only fast neutrons. These fast neutrons have to be slowed down by passing through suitable moderator, say paraffin or heavy water, to get thermal neutrons. For any meaningful study on NAA, the neutron flux has to be above 10^10 or so. It will be highly impossible to keep any gamma or charged particle detector near to the irradiation site because of the damage caused by the neutron bombardment, and NAA is invariably carried out only as an offline technique. The sample after irradiation has to be transported to the counting room where the actual counting setup will be kept in an environment of low neutron background. Appropriate detectors will be used depending on the type of the outgoing particles or radiations being detected. Gamma detectors are usually kept outside the target chamber, whereas charged particle detectors are mounted inside the chamber, which is maintained at high vacuum. The analysis can be prompt analysis or offline analysis. When the radioactivity induced in the target nucleus is comparatively short-lived, the technique is called prompt analysis. In this case, the emitted particles or radiations are detected and counted simultaneously with irradiation. On the other hand, if the activity is long-lived, the counting will be done after irradiating the sample for a reasonably long time in order to build up sufficient activity. The technique is then referred to as offline analysis. These diagrammatic representations give NAA instrumentation for online and offline measurements. Appropriate detectors will be used depending on the type of the outgoing particle or radiations that are being detected. As you can see, the gamma ray detectors are kept outside the target chamber and the charged particle detectors are mounted inside the chamber, which is maintained at high vacuum. Fast neutrons can be obtained in several ways. A simple laboratory source for fast as well as slow neutrons is the so-called neutron howitzer. It consists of a large cylindrical enclosure containing paraffin. There is a central vertical hall extending from the top to the center, where a steel capsule containing a uniform pellet of a mixture of americium-241 alpha source and beryllium is kept. The alpha particles from the radioactive source induces alpha N reactions on beryllium. This reaction is represented as 9Be alpha N 12C, and it produces fast neutrons whose energies extend up to around 12 MeV. The required samples can be irradiated by these fast neutrons by keeping it at a convenient height above the source in the central hall. For slow or thermal neutron irradiation, there are several irradiation ports in the form of vertical halls in the paraffin at different distances from the fast neutron source. The paraffin moderates the fast neutrons to thermal energies. One limitation of the neutron howitzer as a neutron source for NAA is the rather low neutron fluxes that are available. Using a 1 Curie americium-241 source, the maximum fast neutron flux available is only 10⁻⁷ or so, whereas the thermal neutron flux is around 10⁻⁵. Another type of neutron source is accelerator-based sources. In this, a suitable nuclear reaction is used to produce the fast neutrons. A very important source of neutrons, and the one with which probably the largest number of experiments have been carried out, is the 3H-DN4He reaction. The Q value of the reaction is 17.586 MeV, giving the neutron energy around 14 MeV. Deuterons with energies in the range 100 to 200 keV are used in this process, and the cross-section peaks at 107 keV. The reaction is very easily carried out using the Cockcroft-Watson accelerator with a tritium target, and in this case a neutron flux of approximately 10⁻11 can be obtained. Another useful reaction is the 3H-PN3He reaction. The cross-section peaks at 3.2 MeV proton energy, and the Q value is negative 0.764 MeV. The photoneutron sources make use of a photonuclear reaction gamma N using radiative sources such as 22Na and 60Co. The targets are usually 9Be and 2H because of low threshold energies. These yield discrete neutrons of energies up to 0.8 MeV. By far, the most intense flux of neutrons are delivered by the nuclear reactor. This is because the sustained fission process in the reactor releases on the average between 2 to 3 fast neutrons per fission event. For uranium-235, this number is 2.54, and for plutonium-239, it is 2.88. Using the excess neutrons over and above that required for the chain reaction to proceed, a nuclear reactor serves as a fast neutron source. And in this case, fluxes in the range of 10⁻11 to 10⁻13 can be made available. Spontaneous fission sources like californium-242 can be used in NAA, where neutrons emitted is 3.8 per fission. Fast neutron fluxes of the order of 10⁻⁹ neutrons second inverse per Curie of the radioactive source can be obtained. The half-life of the isotope is 2.65 years for alpha decay and 86 years for spontaneous emission. The neutron energy spectrum is continuous with an average energy of 2.3 MeV. Fast neutrons directly delivered by any of these neutron sources can be moderated by passing through a suitable moderator to obtain thermal neutrons. Of course, the flux will be reduced. The nuclear reactors normally contain a thermal column which delivers thermal neutrons by this method. This column consists of a pile of graphite blocks adjacent to the reactor core. The neutron generators will be equipped with a remote controlled mechanism for rapid insertion and removal of the sample to and from the irradiation site. Usually, the sample will be kept inside a polythene container having minimum contamination. Pneumatic rabbit systems are used for transportation of the samples after irradiation. When it comes to detection, the samples are kept in a convenient position in front of the radiation detector in the counting room. For charged particle acceleration, the sample as well as the detector, silicon surface barrier detector, are kept inside a vacuum enclosure. For gamma detection, the vacuum chamber is not required. In this case, high purity germanium detector is used when resolution is important, and sodium iodide detectors are used when counting efficiency is more relevant. The associated electronics for detector signal processing consists of the preamplifier, the main amplifier, and the multi-channel analyzer. This figure shows a typical gamma ray pulse height spectrum obtained when a sample is subjected to neutron activation analysis. The isotopes producing the detected radiations per particles are confirmed by the detected energies as well as by the half-life measurements. The concentrations are obtained from the detected flux values either by relying on a prior calibration using standard samples or by comparison with a standard sample that is irradiated simultaneously with the actual sample and counted using a similar setup. We shall now discuss some of the applications of the neutron activation analysis. Application of 14 MeV neutrons. Using 14 MeV neutrons, boron contents of less than about 400 ppm can be determined by the 11B N-alpha 8Li reaction. Nitrogen can be evaluated, for example in explosives, by means of the 14N, N2N, 13N reaction. Oxygen can be determined, especially in metals, by 16O Np 16N reaction. Elements like silicon, fluorine, phosphorus, which are very difficult to be analyzed by other techniques, can be easily determined by these methods using NAA. NAA technique has been routinely used for the trace studies on petroleum and coal samples, which contain, besides hydrocarbons, traces of sulfur, oxygen, nitrogen, and some metals. These will affect the refining process and the quality of the product. For example, trace contamination by nickel adversely affects the catalysts used in the refining process. Vanadium also is harmful if the concentration is too high. Sulfur in crude oil forms corrosive compounds, damaging the vessel containing the process. In all such cases, the NAA technique becomes very handy. We shall move our discussion to proton-induced X-ray emission, or Pixe, a technique used to determine the elemental makeup of a material or sample. Pixe is by far the most powerful and most widely used trace elemental technique. The idea of using characteristic X-rays for identification of the elements dates back to the pioneering work of Moseley in 1913. Moseley established a relationship between the energy of the X-rays and the atomic number of the atom emitting the X-rays. In 1912, Chadwick had observed and identified X-rays from elements exposed to alpha particles from radioactive sources. Later, when energetic photons became available from particle accelerators, these were used for X-ray production and the capability of the proton-induced X-rays was realized. However, it was much later in the 1970s that the full potential of the process as an elemental analytical technique was realized. It was due to the pioneering work of Johansson and his group at Lund in Sweden, which put the Pixe technique on a solid foundation in the field of trace elemental analysis. Principle: when a material is bombarded with energetic charged particles, the Coulomb interaction between these projectiles and the atomic electrons in the material result in ionization of the atoms. There results a vacancy in the atomic shell involved in the interaction. The subsequent decay of the ionized atoms takes place when electrons from higher shells make a transition to the shell having the vacancy. These transitions can be radiative or non-radiative. In the radiative transitions, the excess energy is emitted in the form of characteristic X-rays with energy given by h nu equal to E1 minus E2. In non-radiative transitions, the excess energy is given to another electron of the atom, which consequently gets dislodged from its shell and emerges out from the atom. This process is called the Auger effect. In radiative transitions, depending on the subshell from which the electron has been removed from the atom as a result of the ionization, K, L, M, etc. X-rays are emitted. Transitions to the K shell results in the K X-rays, that is K alpha, K beta, etc. Similarly, transitions to the L shell leads to the emission of L X-rays, L alpha, L beta, etc. and so on. The energies of the emitted X-rays detected by a suitable X-ray detector give information on the various elements present in the material, and this forms the qualitative analysis. The intensity of the X-rays gives information on the concentration of the elements, and this forms the quantitative analysis. The number of characteristic X-rays is in turn proportional to the amount of the element in the sample. This is given by Nx equal to Np times m n0 over A sigma x t eta. Here Np is the number of protons incident on the sample, m is the amount of the element, n0 the Avogadro number, A the atomic mass number of the element, and T is a correction factor for the attenuation of the X-rays in the sample itself, as well as in any other material in the path of the X-rays like detector cover, etc. Finally, eta gives the detector efficiency. The components that constitute an experimental setup for elemental analysis using Pixe include a Van de Graaff generator or a pelletron, a nickel diffuser foil coupled with a set of collimators for getting a uniform beam of protons, a Pixe chamber in which the sample to be analyzed or the target will be bombarded with a proton beam, and this chamber will be evacuated to a high degree of vacuum, approximately 10 raised to minus 6 torr. And to detect the emitted X-rays from the target, we will be using a SILI X-ray detector and a data acquisition and analysis system. A Faraday cup will be used for incident beam charge measurement. Why do we require a nickel diffuser foil for Pixe technique? For quantitative analysis by the Pixe method, it is necessary that either the target should be of uniform thickness and homogeneous, or that the incident beam should be of uniform intensity across its cross-section, or both. If not, both the beam intensity profile and the target thickness profile should be known. It is very difficult to get uniformly thick and homogeneous targets, nor is it possible to know the target thickness profile. The only way out is to have as nearly uniform a beam as possible. It is for this purpose that the nickel diffuser foil is used before the beam collimators. The target preparation. Usually thin targets having thickness of around 100 microgram per centimeter squares are preferred. In this case, the protons lose only a very small amount of energy inside the target. If the target is thick and the protons lose a considerable amount of energy in the target, then an appropriate integration of the cross-section for X-ray production has to be employed in the equation Nx equal to Np mn0 over A sigma x t eta. Self-supporting target is not always possible for thin targets and some suitable backing may be needed. The backing should be thin so that the proton beam does not suffer appreciable energy loss. And it must also have minimum external impurities due to the possible contamination while the target is being prepared, and should have sufficient mechanical strength to withstand the beam bombardment. Commonly used backings are mylar, Kapton, carbon, foam-ware, nucleopore filter paper, etc. Sample preparation is relatively easy for liquid samples and those which can be brought into liquid form, like water-soluble samples. The water used for this purpose should be double distilled and deionized. When we use a liquid sample, a drop of the solution is put on the backing and allowed to dry up. The dried sample is restricted to be around 2 to 3 mm in size so that it will lie within the uniform portion of the incident beam. Sample preparation has to be done carefully in a clean, dust-free room, and care should be taken to avoid any contamination of the sample. In the case of thick and non-conducting targets, there is an added complication arising from the buildup of charge and voltage on the target. The subsequent electrical discharge to the nearest ground can result in an intense Bremsstrahlung background masking all the characteristic X-ray peaks. One way to overcome this problem is to spray electrons onto the target from an electron gun kept inside the Pixe chamber, thereby neutralizing the proton charge buildup in the target. Detection. The number of X-rays detected can be written as NXZEP equal to KZEP QPM, where Nx is the number of X-rays detected, K is the yield per microgram of the element per microcoulomb of the incident protons, and it is a calibration constant that is to be determined using a number of standard samples. Qp is the total charge collected by the Faraday cup, and knowing Nx and K, and by measuring Qp, the amount of the element M can be estimated. The main features of Pixe. Multi-elemental nature. Using Pixe, all elements present in the sample can be qualitatively estimated simultaneously in one shot. High selectivity. Less than ppm. This is primarily due to the fact that X-ray production cross-sections are much larger as compared to the cross-sections of other processes. Also, cross-sections are smoothly varying functions of the atomic number of the elements and proton energy. Non-destructive nature. It has the possibility of preserving the sample intact for later use. And finally, very small absolute quantities of the elements are required for analysis. Absolute amount as well as picograms can be analyzed under favorable conditions. Limitations of Pixe. The Pixe technique is limited to elements within Z greater than 14 because of heavy attenuation of the X-rays from the lighter elements. For lighter elements, the RBS technique or nuclear reaction technique will have to be utilized. And extreme care is to be taken in the target preparation. Heating due to proton bombardment may lead to evaporation of volatile impurities like selenium. We shall now discuss the applications of Pixe in characterizing water samples and in the investigations using human hair samples and forensic samples. Water samples. Water is an important source of trace elements, both essential as well as otherwise, for our body. Water samples from sources of drinking water like tube wells, rivers, and lakes have been subjected to Pixe analysis. The figure on the right shows a typical spectrum of the water sample from one such source. It is seen that light elements like chlorine, potassium, calcium, zinc, bromide, strontium, lead, etc. and some other heavier elements are present in the sample. The trace elemental content of water is expected to depend on the geographical location. In general, the trace levels are found to increase as we go down the stream from the source of the river. This is expected as increased habitation and industrial and other types of pollution tend to increase the impurity levels in the river water. Concentrations of certain heavy elements will be large near to the cities, especially near to industrial areas. It is a usual practice for factories situated near the river banks to dump waste into the river. The trace levels are observed to be maximum near the site where the effluent is dumped, decreasing as one goes downstream from the dumping location. In another study, samples from a hot spring, well known for its curative properties for skin diseases, was found to contain large sulfur content, a main constituent of skin medications. Human hair samples. Hair is the most easily available biological sample. It contains trace elements which reflect biological processes over long periods of time. Also, continuous exposure to environment leaves an imprint of atmospheric pollutants. In one study, hair samples from different parts of the head of the same person and from different persons were subjected to Pixe analysis. The samples were irradiated as such or after wet acid digestion. The standard deviations in the estimated trace levels were about 17 to 28% in samples from the same person and about 30 to 69% in samples from different individuals. Lead content was more from samples from persons in urban area, undoubtedly from automobile exhaust. Forensic samples. Elemental analysis has been found to be quite helpful in the identification of crime-related samples with possibility of identifying the criminal. For example, in cases of gunshot firing, the type of bullet and distance of firing are important parameters. The bullet carries along with it a part of the primer, gunpowder, and also a part of the material of the gun itself. Some of this get deposited around the bullet hole on the body of the victim. An analysis of radial distribution of these elements, antimony, barium, copper, lead and iron, can be helpful in this aspect. The non-destructive nature of the Pixe technique becomes handy in such analysis.